so I can kind of get a sense. You have a lecture on discrete sampling already, right? Kind of. More or less. Introduce it. Okay. So we're gonna go and dive into discrete sampling quite a bit. So okay. So because this is gonna be a kind of a long lecture, I'm gonna give a little bit of a roadmap, and I apologize. I didn't know there were 2 slides. I'm gonna refrain from using the laser. So roadmap. We're gonna talk about a little bit about aliasing, and we'll illustrate this with a demonstration. And then we're gonna talk about the Nyquist-Shannon sampling theorem. We're gonna talk about how we can express it in the folding diagram. And then we're going to talk about how can we apply this and what is the application of discrete sampling. We're going to follow to introducing the Z-transform, which is the representation in the mathematical domain of discrete sampling, kind of a parallel to the Laplace transform. And finally, we're going to look into how to actually interpret the results from the Z-transform. So I'm going to first start with a demonstration. And I apologize for you guys that are sitting far. The demonstration is not that large, and so this means that you might want to come closer if you want to see anything. So I'm going to turn off the lights. And also this one. So if you look over here, and forgive the crude of the model, I don't have time to put it to scale or but of course, it does the job. So this is it's a very simple model. It has little tank, little pump. The pump pumps the water, and it just recirculates and generates a jet. And then you might ask me, why is a jet interesting, right? What is interesting about the jet? So I'm going to turn it on, and hopefully it's doing what it's supposed to do. Yeah. So can anyone here explain what's kind of going on and maybe no? Yeah. So has anyone seen this in person or just on YouTube? Maybe. Yes. No. Well, you've already seen it, so you can. Anyone has already seen this on YouTube? Yeah. Cool. Yeah. So fortunately, because of the internet, we can have the possibility of seeing all of these things. But I find it personally very cool to see this in person. And the fact that the water is moving up instead of going down is kind of mind-blowing. If we change the flashing frequency of the LED, we can make the water look like it's standing still. If now we change the frequency a little bit more, it looks like it's falling in slow motion. So this is a phenomenon that is occurring faster than we can see, but because of the LED flashing frequency, it's showing the phenomenon to us in a weird way that is, we're gonna look into that. So this is an effect of sampling. The fact that the LED is flashing very rapidly at the frequency that somehow matches the frequency of the formation of the droplets. And I see that you're taking a movie, yeah. So you probably are seeing some artifacts from your camera, right? So if I change the frequency, you're gonna see a rolling shutter kind of rolling up, right?
You called it.
Yeah. So yeah, I've already done that. So of course the camera has its own sampling rate, and then now the mismatch between the rate of the flashing on the LED and the rate of the capture of the frames in the camera generates another artifact. Okay, so this is, I hope you appreciate this as much as I do. Now we're going to go back to the lecture. I should probably turn that off. Turn it off. For you the late ones, I'm going to show, because I have a little backup video. Since I wasn't confident that everyone would be able to see this. So this is a video captured with a high-speed camera. It's captured at 840 frames per second. And of course, because the phenomenon is happening at this lower frequency, we can see the entirety of the phenomenon. And this is how. So From the fluid's perspective, it's even cooler because generating droplets at a constant rate is not something very easy to do. But here we're not, I'm not going to talk about the fluids part, I'm going to talk about the controls part. Okay, so let's analyze this to kind of have a sense of what's going on and describe it in a more formal way. So every strip here is a frame, and I'm showing every second frame of the video, of the camera. And so it was sampled at 840 frames per second. Now I'm showing at 420. And the yellow dotted dashed lines, they show the true trajectory of the droplets. And as you can see, the sequence shows, if you follow the droplet, the sequence would show the true trajectory of the droplet. If we focus on only a single droplet or a strip between two droplets, we can draw a waveform. Because it's kind of hard to assess this because it's a sequence of images. So we're going to focus on a single droplet trajectory. And as you can see here, each droplet is a symbol. And if we draw the line that connects the droplets, we can reconstruct a waveform that resembles the true waveform. The true waveform is shown in the dashed line, and it has the kink, which we can't capture because we miss when this droplet leaves the frame and the next droplet enters the frame. But we can reconstruct the wave pretty well. If we decrease the sampling rate, so now I'm decreasing the sampling rate, having it once again to 210 frames per second, then that's the true trajectory of the droplets. If now we focus at 1, this is how it looks like, and if we connect the dots, then the sawtooth wave looks a little bit more jagged because we have less samples to reconstruct. If we do it once again, so now I'm having the sampling rate once more, and I'm showing every 8 frame, and you see the true trajectory. And now if you look at the movie, it's kind of hard to see what is the direction the droplets are going. If we focus on the sawtooth waveform, you can see that we can get the frequency of the sawtooth right, but now it's a little bit difficult to understand what is the wave. It's very jagged because we only have 2 samples per cycle. So what's going to happen if we reduce the sampling rate even further? Anyone has?
It's going to be a straight line.
What is that?
It's going to be a straight line.
It might become a straight line, but before it does become a straight line, so I'm actually showing, instead of, that's actually good. If I have it once again, it would look like a straight line, but I'm not having it. I'm just showing every 13th instead of 14th frame. And if you see here, now it looks like the droplets are going up. So this is the effect that you're seeing when I'm flashing the LED at a frequency that is very close to the frequency of the formation of the droplets. If now we show the waveform, we can see that the waveform now looks at the wrong frequency, and also the droplet direction looks wrong. So we got both the frequency and the direction of the movement wrong. Okay, so now if we show every 14th frame, then you can see the droplets look like they're not moving. And this would be just because we're flashing the LED exactly at the frequency of the formation. So then we freeze the phase and we capture the phenomenon always at the same phase angle. Therefore, it doesn't look like it's moving. And of course, this only works for phenomena that have single frequencies. And once again, if we now show every 15th frame, it looks like they're going slowly down. We got the direction right now, but now the frequency is wrong. So how are we going to describe this and have this kind of a more abstract picture in mind of how this phenomenon is happening? And hopefully I inspired you to kind of try to understand this phenomenon, given that it's qualitatively interesting. So, okay, so what I'm gonna present is what's called the folding diagram. And in the y-axis, I have the frequency that it appears to us as we sample the phenomenon. And in the x-axis, I'm going to show the true frequency of the phenomenon. And the 45-degree line is the line where we got everything right. Basically, the true frequency of the phenomenon is the frequency that it looks like as we sample it. So I'm going to add a line here, which is a limit for our sampling device. And I'm going to claim here that the limit is half of the sampling frequency. We're going to prove that mathematically shortly. Well, not shortly, but eventually. So, but I guess you kind of have a sense that there should be a limit to how, what are the frequencies that we can resolve. Because we're sampling at a given rate. We can't resolve anything faster than the sampling frequency. That stands to reason. And it turns out that you need at least 2 samples to resolve a phenomenon, or the frequency of the phenomenon. So that's why a factor of 2 comes into play. So this means that if we're within the ceiling, we get the frequencies right. And here is an example of how it looks like if the true frequency of the phenomenon is low in comparison to half of the sampling frequency. We get a lot of samples, and then we can easily reconstruct the waveform. If we increase the frequency of the phenomenon, then we get less samples, but we still get a few samples per cycle, which allows us to reconstruct the phenomenon, assuming the phenomenon has only a single tone, which is actually quite important. If we now match the ceiling frequency with the frequency or the maximum frequency that you can capture, we get 2 samples per cycle, which means that now we can, if we connect the dots, we can reconstruct a triangle wave that resembles our sine wave, and we can get the frequency right still. But what happens if now we increase it even further? Well, I claim here that this diagram, it's called the folding diagram because it folds. So now we get all the frequencies of the true phenomenon that are above the sampling frequency, they fold back into the frequencies that we can resolve. And here I'm going to show an example of how it looks like. So if we're within the sampling frequency and half of the sampling frequency, we miss almost a full cycle, which means that the position of the samples slowly drifts, and then we get this low frequency behavior. I'm not going to show what happens over here because it's kind of hard to understand. So this one is kind of easier to understand graphically. And if we're now sitting exactly at the sampling frequency, then we get 1 sample every phase of the cycle, and that looks like the droplets are just standing still. And this keeps on folding back and forth ad infinitum. And this is important because any phenomenon can have whatever frequencies. We can have frequencies on our electrical signals of megahertz, gigahertz, and those frequencies, they're there. Since we're sampling at a finite sampling frequency, those frequencies are going to appear within our sampling bounds, but they're going to appear, they're going to be wrong. So we need to remove this frequency content, and this is kind of the takeaway of this chart. In order to get our sampling right, we need to remove the content above half of the sampling frequency. So we're not fooling ourselves into believing that a tone that is in the gigahertz range is actually shows up as a tone within our measurement bounds. So that's why we need to filter the signals before we feed them into our digital to analog converter. Sorry, analog to digital. Okay, so I'm gonna call this frequency the Nyquist frequency, and I'm pretty sure you've already heard about the Nyquist frequency. It's half of the sampling frequency, and it's named over the guy that discovered or proved that this is a thing. So here we have in this diagram we have several regions. So if we're in the first region, we got everything right, we're fine. If we're in the red regions, which are labeled as folding, then what happens is we get not only the frequency wrong, but also the direction of the phenomenon wrong. So we got the phase are rotating in the opposite direction as it is rotating. Or if you will, the frequencies look like they're negative. That's another interpretation. If we're in the yellow region, then we get aliasing, and aliasing, in aliasing you get the frequency wrong, but the direction of the phenomenon is correctly sampled or correctly interpreted. So for this first part of the lecture, you can forget everything, but just remember that the Nyquist frequency is half of the sampling frequency, and that if you're sampling at a given sampling frequency, you gotta remove the content at higher frequencies higher than the Nyquist, so you can be sure that you're not fooling yourself into believing a tone or a frequency is present in your signal, which it isn't. And this can destabilize the control system, of course. course, because if you're measuring something that is, you're trying to respond to a low frequency phenomenon because you think it's low frequency, but it's actually high frequency. Okay, so now we're gonna move a little bit into attempting to define mathematically what's the discrete time version of the Laplace transform, so we can do analysis similar to the Laplace domain analysis that you've already learned in this class. So first I'm gonna talk a little bit about how this goes into implementation, into hardware. So you design your control law, and you want to implement in hardware, right? That's our goal as engineers. We design something and we want to make it, we want to build it, right? But with the things you learned so far, which are the S domain analysis, you can only build a subset of controllers. And the subset needs to lie in the analog domain, which means that if you were to build an electronic circuit, it would have to look like this. So it's a set of analog amplifiers. Each amplifier does a role, integrating or differentiating, and the values of the resistors correspond to the cutoff frequencies of the filters and everything. And of course, if you want to change the characteristics of your digital controller, you're going to have to change the values of the components, which is not very handy. So I got no problems with analog circuits, as you can see here in my t-shirt. But now we're in the digital era, and we can do better. We can afford more flexibility. And it's a trade-off. We're going to have to trade off flexibility, which is a good thing, for these limitations on the sampling, which are going to limit the capacity of our circuits. And this is how it's going to look like. So you can implement it in hardware if you're in the hobby level, or you're just doing a student project. You're going to use a hobby Arduino thing, or a Teensy, or something that is available, and they're pretty powerful nowadays. But if you're in the industry, you're going to need something more robust. So you're going to need a programmable logic controller, which is way more suitable for industrial applications because it has a lot of devices built in to make sure it doesn't fail. It's noise proof, all the noise in industrial sites and everything. Okay, so I'm gonna remind you of the feedback controller, and maybe I can kind of quiz you a little bit. So what would be D of S? That would be your controller, exactly. And G of S? Plant. And H of S? Yeah, it's the sensor or the measurement device. So we have here a control input signal, R of S. We subtract the measured value of our sensor, and then we get an error. This error signal goes to the controller, becomes a control input. Control input goes to the plant. The plant does its thing. And then Y is just the state of the plant. We want to measure the state of the plant. You usually, I think in this class, you're ignoring H of S and you're just saying H of S is 1. But in reality, it might not be the case. And this is kind of a general sense of how the controller looks like. And we want to know where our Arduino is sitting, right? So our Arduino is sitting in this box. So it's doing the subtraction operation, and it's also computing the control input. So it's doing both the plus or minus sign and the. So let's expand it. And I'm going to shift here to time domain because frequency domain is kind of difficult to show the components inside the box. So we have a signal R of t and a measurement M of t. And we want to compute a control input U of t. So for that, our Arduino, it can only do stuff in finite time or finite cycles. So we're sampling at some sampling rate. So the switch here, it represents our sampler. So our sampler is taking a measurement and then holding it somehow for our Arduino to perform its computations. So this means that our signal from the continuous time now becomes a signal in the discrete time, R of k capital T, where k is an integer number and capital T is the sampling period. And of course, this is something about the digital controllers. We need something to convert this analog signal into a digital number. So for that we use an analog to digital converter, ABC. And I must say that in most practical applications, it doesn't make too much sense to have R of t getting in, because we usually have the desired control state in the memory of the controller, in the digital controller. So I'm replacing R of t as a number that comes from the memory. And this is the case even because even if you don't have something just in hard-coded in your code, you can have like the user just type in a number in a keyboard, and that's going to go to the memory. It's not going to be an analog signal. Right? So it makes sense to replace this block as a memory block. And then we perform our computations. So the computation includes measuring the error, or computing the error, and then doing some calculations. We can use past values that we can store in our memory. We perform some calculations, and now we want to come up with a u of t. So I'm going to have to expand a little bit because I'm running out of space. So we have the discrete control input u of kt, and now we have to go from discrete time back to continuous time. So for that, we have to convert the signal from the digital domain to the analog domain, but also we have to hold the signal. Hold the signal means I have a number, and while I'm doing my calculations for the next number, I have to hold this number in the output such that the controller knows what to do between calculations. So this is what I mean by holding. So now we can replace this, which is kind of a detailed version, with just a set of blocks. So we have d of z, which is our controller. We have the sampler, and we have a zero order hold. You don't need a zero order hold. You can have a first order, second order hold. It doesn't. It depends on what you want to do, but in most practical applications, it's going to be zero order. And zero order means exactly just hold it until the next sample. Don't do any interpolation. Okay, so this is how it looks like. And I just want to highlight that, as I said, we're computing numbers, but it takes time to compute the numbers, which means that we're introducing a delay. So every time we hold the signal to the plant, and the measurement is available already, of course, given the restrictions of the analog domain, but the measurement is always available. But I can't use this measurement while I'm computing. So this means that I'm introducing a delay of capital T, which is also going to have some important impact, or depending on the sampling rate, some impact on the characteristics of the controller, which we must include. Okay, so I described it qualitatively, and now we want to have some sort of mathematical tool that allows us to analyze this control system. So here I have a random analog signal, and we would like to take a sample, right? So mathematically, how can we take a sample of a continuous signal? Does anyone have an idea of how can I perform a mathematical operation that takes a sample of the signal? Anyone? No? Kind of a special function that I can multiply this function by? It's difficult, yeah. I mean, this guy kind of came up with this, and it's not straightforward. So I'm sure, or maybe not, but how many of you have heard about the Dirac delta function? So the Dirac delta function is an infinitely short impulse. So if I multiply this infinitely short impulse by the function, it's like taking a sample. So I'm going to show here. Let's say I have a delta function, and the delta function looks like just an impulse at the origin. If I want to take a sample, what I do is I multiply the delta function by my function, and I get a sample. 1 point. But we can't do too much with 1 point, right? It's just 1 point. We can't do anything with it. So it's kind of lame. We need more points. So for that, we need what's called a Dirac comb, which is a set of delta functions spaced by the sampling time. And it's like a comb, right? It looks like a comb. And this is the mathematical definition. So we have the summation of the delta functions delayed by k, which is some integer number, times capital T, which is the sampling period. and we do that however many samples we want. And if we multiply the delta function or the set of delta functions by our continuous function, we get several samples. And this is how it looks mathematically, it's just a multiplication of the two. And the cool part is now we have a function to work with. So we can take the Laplace transform of this function. And there's a little trick before we take the Laplace transform, which is realizing that after multiplying this, the function it doesn't matter if the function is in the analog domain or if it's in the already sample domain, because after multiplying these two together, the function is not going to be defined between the samples. So this means that I can just bring it in and replace t in the continuous time by kt, which is the discrete time, k capital T. Okay, so now we can do the Laplace transform. So what's the definition of the Laplace transform? Anyone? What is that? Yeah, but how do we mathematically define? E to the minus st dt. Yeah, that's the integral from 0 to infinity of whatever is inside the bracket times e to the minus st dt. So let's do that. So integral from 0 to infinity e to the minus st dt. Everything else in brackets is just pop. So there's a few mathematical tricks we can do here. We can swap the summation and the integral signs. This is allowed because both are sums, so we can do that. And we can, and this is kind of a little bit beyond, I guess, but we can also realize that after we swap them, that f of kt is not a function of small t anymore, so we can bring it up. So now we have our summation sign and an integral that involves only delta and e to the minus st. And I'm not going to pretend that I know the result of this integral. You just plug it in Wolfram, and you get the answer. But the answer is pretty cool, because it is e to the minus kst times a unit step of kt. But kt is always positive, which means that the unit step is always 1. So we can just get rid of it. And then we plug it back in, and we get e to the minus kst times the summation. And we're almost there. So the only thing we need to do now, kind of to go back to the textbook definition of the Z-transform, is to replace f of kt by f bracket and square brackets n. And it's not that n is kt, it's just that nth sample, the square brackets means the nth sample of f in the discrete domain. And k, and let's just replace k by n, which we can do, but bear in mind that this n is not kt, it's just k. So if we do that, we get the nth sample of f times e to the minus st, nst. Now we're going to introduce the infamous dummy variable z, where z is e to the st. And if we do that and we replace it in the expression, then we get what is the definition of the z transform. The discrete version fd of z is f of n times z to the minus n, summation from 0 to infinity. And this might not make too much sense, but this is quite an important discovery, and I think you can, again, finishing this part of the lecture, you can remember, you can forget everything about the derivation. The only thing you need to kind of remember is, okay, so the Z-transform, it is a mathematical way of modeling a similar transformation to the Laplace transform, and it does correlate to the Laplace transform through the Dirac column. That's the only thing you kind of need to remember, and of course, the definition of Z, that might be handy maybe in the exam. I'm not sure if Dr. Hubicki is going to use this in an exam, but it's not up to me. Cool. So now, of course, we're going to, I want to get a feeling of what the Z-transform is doing, right? And the Z-transform is what we call a conformal map. So what is the Z-transform actually doing? And I found this quite a catchy expression, so I decided to make like a kind of a YouTube clickbait thing. What is the Z-transform actually doing? And hopefully we're going to get millions of clicks with this clickbait and pretend that this is more interesting and more fun than it actually is. So, as I said, the Z transform is what we call a conformal map. And maybe you haven't heard about this expression, but the conformal map is a means of transforming a complex plane into another complex plane through a mathematical expression, in this case, z equals e to the st. And this is going to turn out to be a conformal mapping from Cartesian to polar. So here I have the S-plane, and I have here just a little bit of the plane. This is the imaginary axis. This is the real axis. And maybe you can tell me what happens when I'm in the right-hand side of the plane. It's unstable. If I'm in the left-hand side, then I get a decaying signal or decayed sinusoid. If I'm sitting in the real axis, in the stable side, what do I get? What is that? No oscillation, exactly. It's just exponential decay. And if I have any finite complex number, then I get some oscillation, right? So, as I said, the Z transform is a map from the S plane to a different plane, the Z plane. So the map looks like this. So this is a little animation showing where every feature of the complex plane lands when we go to the Z plane. So it's kind of like a warping of the Z plane. So the right-hand side warps outwards. The left-hand side fits all inside the circle. This would be the unit circle, as we're going to see. And we have a stitch at the Nyquist limit. So it kind of stitches onto itself. We're going to see that this is not really a stitch. It's actually a branch cut. But this is kind of complex analysis. It's kind of complex. We're not going to handle too much, but I'm going to kind of give you a hint of what's three. So, okay, so we have a map, the Z map, that folds our S plane into the Z plane. So let's analyze slowly and carefully what it's actually doing, so we can get a sense of where the important lines on the S plane land in the Z plane. So the stability line, which is the line that corresponds to the Fourier transform, where we have no real part, no decay, no growth, only oscillations, and the oscillations happens at a frequency of omega. If we do z equals z to the st, then we get z equals e to the I omega t. And what is e to the I omega t? Anyone? Where do you think it lands? What is that? No, it's e to the I omega, right? So omega t, omega can be anything. T is our sampling time, right? Or our sampling period. So this means that omega t is a number, any real number. So e to the I, e to the I and times some real number is just a phasor that goes around the circle. Somewhere in the circle, lands somewhere in the circle given omega. So it's always at the unit circle. If you think about it, it might not be straightforward, and you kind of have to rehearse it a little bit. But it always e to the I something is always a phasor of unit length that goes around the circle. Okay, this is kind of the easy part. So if we now look at the positive real axis, where we have exponential growth, but we don't have any oscillations, right? So what happens is, S is a real number plus no imaginary part. So then Z equal e to the st is just Z equal e to the at. And e to the at is an exponentially growing number, but it's real. And it's always greater than 1 because a is always greater than 0. So this means that it lands at the real line, positive real line, but always greater than 1. So this line here ends up over here. And you remember the mapping, it kind of folded. It didn't really move while it was, it just shrunk a little bit. So For the negative part of the real axis where we have exponential decay, then we get z equals z to the st, but now a is less than 0, which means that we get a number that is always real and less than 1, which means that it lies between 0 and 1. So all of from 0 to negative infinity, all gets crushed into a line between, a segment between 0 and 1. Okay, now let's expand a little bit and look at the left-hand plane, where it might oscillate. So in that case, I have some general expression, a plus or minus omega I, where a is less than 0. I apply the map, and I get e. I'm separating here the real part, which is e to the at. That part is always decaying. And e to the plus or minus I omega t, as we discussed, is something going around the circle that has unit magnitude. So this means that we have a number that is always less than 1, multiplying a number that is around the circle, but always has unit magnitude. So this means that it's going to land inside the circle. If now we look at the right-hand side of the plane, we apply the map again, and we get the same expression, but now a is greater than 0, which means that now this phasor that goes around the circle, it's multiplied by a number that is always greater than 1, because a is positive. So this means that where does it land? Any guesses? Outside the unit circle. Exactly. So everywhere else outside the unit circle. Okay. So we explored pretty much all of the estimating, except for a detail. So we actually looked only between the Nyquist limits, which I'm going to claim is I pi over t plus a, and we're going to see this. So the region I'm talking about is above the Nyquist limit, we have some frequencies that we can't resolve, as I was discussing, right? So this is kind of tricky, but so the Nyquist frequency is half of the sampling frequency. So the sampling period is 1 over the frequency. So this means that the Nyquist frequency is 1 over 2 capital T. The S-plane is actually in radian frequencies. So this means that we have to convert the frequency of Nyquist to the radian frequency, omega Nyquist. And that's just 2 pi times the frequency. So if you do 2 pi times the frequency, you get 2 pi over 2t, and that's pi over t. That's where the I pi over t comes from. So I is the oscillatory part, and pi over t is the Nyquist limit. And A can be anything. It can be anything real, positive or negative. Doesn't make sense. So now if we apply the map, we have S equals A plus or minus omega I, where omega is always greater than the Nyquist frequency. And in this case, the Nyquist frequency is pi over t, so this means that omega is always greater than pi over t. If we do that, and we apply the Z transform, then we get I omega t, but omega is always greater than pi over t. So this means that I can express, because it's greater than pi over t, I can express it as some apparent frequency, which is less than pi over t, plus some integer number times pi over t. And if I do that, then, and M here represents how many folds I have in the folding diagram. So if I do that, then I'm just separating here the exponential, so this is I omega, e to the I omega t, so I get e to the plus or minus I omega a t, and e plus or minus I m pi. And you got to realize that e to the I m pi is always positive 1 or negative 1. Because the angle pi is always, well, pi is 180 degrees, so this means the phasor is pointing in the left-hand direction. And since it's always magnitude 1, that would be negative 1. If you have 2 pi, then you're pointing at the positive direction, and then you get positive 1. And you keep going around, right? So I can replace that by just minus 1 to begin with. So I'm going to copy that expression over here, and I'm going to compare this with the cases where we were inside the Nyquist limit, where it looks exactly the same. And if you compare the expressions, they're exactly the same, except for the minus 1 factor. So this means that the frequencies above the Nyquist limit, they're actually landing exactly where the frequencies inside the Nyquist limit land. So the Z transform, it folds on itself. And I think it makes sense to watch the animation again, but now with frequencies above the Nyquist limit. Because the animation that I showed before, I suppressed the frequencies above the Nyquist limit. So if we do that, you're going to see the same animation, but now the frequencies above the Nyquist limit, they're coming in, and it is a little bit overwhelming. And this happens over and over. I'm showing only two folds in the folding diagram, but they land exactly at the same point. And this kind of proves that the Nyquist sampling theorem actually comes from the Z transform, and it correlates, kind of ties everything all back together. Cool. So you're going to ask me, okay, so you showed me all of this math. It's beautiful, but I just wanted to program my Arduino. I just want to implement, right? So we're gonna do a little bit of an exercise of how it looks like when we attempt to implement this. So first we're gonna start looking at PI controller, which is kind of a good example to start with. So if I were to ask you, what is the definition of the PI controller in the S domain? What is the transfer function of the PI controller?
0 order.
KP plus I over S, KI over S?
KP plus KI over S. Exactly. That's pretty good. So D of S is KP plus KI over S. I do a little bit of math, and I'm just shuffling around to expose the pole and the 0. Okay, so we have to kind of realize that the controller D of S is getting an error and is converting that into a control input. So in a sense, it's a filter. It's a digital filter now because it's going to be a digital filter. Now it's an analog filter. So how does it implement this filter is what we're going to explore. So as I said, it gets an output, and divided by the input is the transfer function, and then we just get the transfer function of the PI controller. Which means that we can turn this, and I don't know if Dr. Hubicki talked about this at all in the lecture, but this actually defines a differential equation. I don't know if you can see this in this form, but we can just move around a little bit. Move the S to the left-hand side, you get S E of S. Move the E of S to the right-hand side, and you get KPS E of S plus KI E of S. So this, I suppose you can see now it's a differential equation. And how do we, if we do an inverse Laplace transform, how would it look like, assuming zero initial conditions? Anyone has a kind of a guess?
U dot P.
That's U dot, exactly. This guy?
U dot.
Yeah, KP times E dot, and that's just E, right? E of T. So then we get U dot, KP, E dot, plus KI E. And this is what we call the velocity form of the PI controller. And it computes the derivative of the control input. But most of the times we're not too interested in the derivative of the control input. We're actually interested in the control input itself. So we need to integrate this once. So let's integrate it. So we integrate U dot, and we get U. Integrate E dot, you get E. This E here we can't integrate, so we have to leave it as the integral form with the dummy variable tau instead of T. And this is what's regarded in the literature as the position form of the PI control. So it's just a distinction between how we compute it. It has the same behavior, the same characteristics. Okay, so now we have to kind of realize that we can't really compute this integral in the digital controller because the integral is a continuous piece. Right? So we are missing stuff in between that we have to approximate. So we can only hope to approximate the integral given our samples. So this means that, remembering the chart of the, I'm calling E of T instead of F of T, I can only approximate this integral. And so let's do a little bit of an exercise. So this is kind of a more complete version. I have here from 0 to 11t. And let's say we're at t equals 11t, and we want to approximate the integral. How would you do that? So the first thing you kind of have to realize is we have 11 integrals, but we have 12 symbols. So this means we got to drop one symbol. Otherwise, our integrals, if we just add them all up and take the average, that wouldn't be enough, right? Because we would exceed the integral by one symbol. So you have to drop a symbol. So this means if we're sitting at t equals 11t, we have to either use the sample, and then extrapolate that the integral is going to be like this, or some interpolation of this to the future, extrapolation of this to the future, or we're going to have to drop the sample, and then use this as interpolation with the past data. So this means that we have some kind of methods that we can use for integrating that depend on your application, really. So three methods I think probably Dr. Hubicki is going to cover. Those are called the forward Euler, which means we're going to use forward rectangular windows. So we drop the last sample and then we integrate forward. We can drop the last sample and then integrate backwards. Or we can use Tustin's rule. It's called Tustin's rule, or not Justin's rule, Tustin's rule. And this is just trapezoidal integration, where you average the 2 points to come up with a single point, and then if you have 12 points and you take averages between them, you get 11 points. That would be enough for the integration. We're going to look only at backwards Euler, and the reason for that is because we can't really predict the future. So forward integration doesn't make too much sense, because in a real controller, you can't really assume stuff about the future. You can, but there's caveats to that. So we're gonna stick to what is easier to do, which is the backwards integration, which is what we're gonna call causal. So let's approximate the derivative so we can kind of use the differential equations that we discussed. So here I have a derivative at 11t, and we're using backwards Euler, which means that we're using the current data point and the past data point to approximate the derivative. So can anyone tell me what would be the derivative here?
1. You went from 10 to 1 in one sample, 10 to 11 in one sample period.
Oh, I get your point, but no, you'll be
that's
right.
the
This is like the 11t sample of E. You don't know the value here.
Yeah, we
it's
don't
just
know
a general value, right?
So we don't know. It looks like it's.
Well, you don't know the numerical value, but how would you come up with an expression for it?
Yeah, delta E over delta.
Exactly, delta E over delta t. So we can do that on the board, and it might make more sense. So the derivative E dot of t, we're going to approximate as delta E on delta t, right? So what's delta E?
E2 minus E1.
Well, at 11t, let's assume that we're at 11t. That would be E of 11t minus E of 10t. That's delta E. And what's delta t?
1. T.
It's capital T, the sampling period. So we only have samples between the periods. So this means 11t minus 10t is t. So that's capital T. So that's what comes in the next part of the slide. So, of course, this only applies to 11t. And we want to do a more general definition. So we just replace the 11 with k, and then we get kt, and kt minus capital T would be the previous sample. Okay, so we have these approximations of the derivatives. I computed the derivative of u dot, and I'm going to copy the expression of, the differential equation that we came up with to replace the approximations and compute what is the control input of the control. And as I discussed before, we're doing backwards Euler instead of forwards Euler, but in a digital filter where you're just analyzing the data and you're not really controlling the system, you would be able to have data from the future sample, because all the data has already been recorded. But in our case, because we're doing an online digital filter instead of an offline digital filter, then we have to consider that we don't have the future sample. So now let's go back to our differential equation. U dot, we're going to replace our approximation of U dot and our approximations of U dot. And if we do that and we plug in the approximations, we get this expression. It looks a little bit nasty. It's going to become nastier. Not too nasty. But, so I'm going to copy that expression just kind of to have more space in the slide. I'm going to replace KT with N, as we discussed, because then we can go back to the Z transform and tie everything back together and see what the Z transform actually does in our analysis. So U of KT becomes U of N, the nth U sample, and U of KT minus T becomes U of N minus 1, which is the N minus 1th sample. And we do that for E of T, and we get that. And now we do some crunching, and I'm gonna spare you the details. You move around the T's, and then you isolate U of N. You move the U of N minus 1 to the right-hand side, and hopefully you can follow this, you get an expression. And you can do this in general. You can do this for any controller. You can do it for a PAT controller, a lead lag, whatever you want. But the important part is now we accomplished something. Can you realize what we accomplished with this? There's something very important about this expression.
U of N can be calculated now from discrete samples.
From the past samples.
Past samples, yeah.
Right? From the current measurement, which is E of N embeds the current measurement, and the past errors and the past control inputs. So this means that now we can implement this in code. So let's kind of just have a look at how a code controller would look like. So we can have as much stuff as we want in the memory. So I'm storing in memory the relevant variables, which are E of N minus 1, the last error, the current error, and U of N minus 1. Those are the numbers that show in the expression. I use my fancy expression to compute that. This is literally one line of code, right? And I get the control input. I update my control input, and I loop around. This is literally a for loop. I change U of N minus 1 to U of N, change E of N minus 1 to E of N, and get the next measurement to compute E of N. And I just do this in a for loop, and I got my controller working. So this is how it might look a little bit elusive, but I hope you kind of can see how this can be implemented in code. Because when I was taking lectures about this, I always had an issue. How do I translate my controller into actual code? This is how we do that. Okay, so now we went through the implementation details, and now we can do some analysis. So we have the discrete time version of our controller, and we can use the Z transform, our new fancy tool, to analyze it. So it's kind of difficult, but you can kind of realize that the Z transform of this expression would give us the Z plane behavior of our controller. And in this case, the Z transform of U of N is similarly to the Laplace domain, is just capital U of Z. Similarly for E, it's just capital E of Z. This guy here is a little bit tricky, so I'm gonna have to spare you the details. So U of Z comes from U of N, U of Z comes from U of N, the constants just carry over. But E of N minus 1, I'm claiming here it's E of Z times Z to the minus 1, or 1 over Z if you will. And this minus 1 means the last sample. And this is the proof. I'm not going to go through the details, but you can stare. If you stare for long enough, you're gonna be able to believe. I might place this lecture notes if you wanna kind of understand what's going on over here. But this exponent minus 1, it can be minus n for the nth past sample. So if you have like 5 samples behind it, it would be z to the minus 5. If you have samples in the future, you just replace this to the z to the positive 1, and then you get the future 1 sample. Okay, so we do that. We do some mathematical handling of this expression, and we come up with a transfer function very similar to what we do in the Laplace domain. And this transfer function of U of Z on U of Z is this guy. And it looks very similar to the Laplace domain version. So in the Laplace domain, I think I'm going to have that. So I'm going to copy that. Oops. So in the Laplace domain, we had Kp times S plus a ratio between Ki and Kp over S. In the Z domain, we have Z instead of S, some number, and then some other constant, and those constants depend on the PID tuning that you're doing. But now we have capital T in the expression, and capital T is the sampling time. So this means that now this capital T, or the sampling timer, is going to change the location of our zero, which is going to affect the performance of our controller. As you might remember, changing poles and zeros changes the performance through the root locus. You can see where they're going to go, right? So this is what we're going to do a little bit. Well, not quite, because this is actually a rather complex subject, but I can kind of just reminding you. So where do the zeros and the poles of this open loop controller end up? Do you kind of remember? If you were to draw the poles and the zeros here?
Just go from the origin out to.
So you said?
You have a fold 0 and 0 -5 and
Awesome. Yes, exactly. So a pole at 0 and a 0 at minus Ki on Kp, which is actually in the stable region, right? So now we can do the same for our D of Z, which is our controller in the discrete domain. And if we do that, we get this expression where the pole length is exactly at +1. And the 0 lands at, well, you make this expression equal 0, and then you find out where it is. It's kind of a nasty expression. But it lands inside the stable, I should have been. It always lands inside of the stable zone as long as you have positive Kp in here. So just forget about that. But the expression is correct. This pole here, it moves around and it always stays between 0 and 1. And it's not straightforward what it's going to do with our system, because we need to include the system, the plant, and then we need to close the feedback loop. These are the open loop poles. So here I'm going to show you just kind of an example of what a PI controller does, continuous versus discrete. So in the continuous time, I might actually move here so I don't occlude too much. So these are our controller poles. These are the plant poles. The plant is a second order damped, but not a critically damped system. And so we have the plant poles, we have the zeros, we close the loop, and we get the root locus diagram. I'm sure you all remember this diagram. So what happens is the poles go to the zeros, and these poles go to infinity. But you see that the poles always stay in the stable region. So this means that the PI controller with these characteristics, which are handpicked, to be honest, they always make the system stable. But if we use the same system, the same plant, so now the plant poles are sitting here, the zero and the pole of the controller are sitting here, and we're gonna, maybe Dr. Hubicki is gonna cover in the future, but to the discrete version of the plant will have zeros at Nyquist. So the zeros of the plant now go to the Nyquist. One goes to the Nyquist and the other goes to infinity. But this dashed circle is the stability bound. Everything inside the circle is stable. So the plant poles of the closed loop, the poles of the closed loop system, now they have a stable region, but they become unstable. So our discrete controller, it can destabilize the plant by just the virtue of discretization. And this is one of the caveats that we have when we're doing discrete domain analysis, and this is why it's important. Okay, so this is pretty much it that I have for today. So just kind of covering and concluding the talk. We covered aliasing and folding and the Nyquist limit. We covered the definition of the Z-transform. We looked at the Z-plane. And then we did backwards Euler, which is one of the discrete integration schemes that we can have. We can have forms and Custom's rule. Not sure if Dr. Hubicki is going to cover any of those. Probably. at least one of them. And with this, I'm gonna finish and hopefully you like it. So do you have any questions or anything if you wanna discuss or anything? No? You're free to leave. That was an early one. That's good.
What?